Good day, I'm Norman Wildberger. Today we're going to start trying to extend arithmetic from the rational number setting, which is very familiar, to a slightly larger framework which includes some new object, or perhaps objects, that play the role of infinity in some sense. And of course, since this is a foundational series, we want to lay things out in such a way that it's completely cut and dried, so that there's no philosophizing necessary at all, and so that the meaning is completely clear of all the terms that we're using. So this is motivated by what we've been doing in terms of on sequences. We were talking about on sequences generated by rational polynumbers. A polynumber over another polynumber gives us a rational polynumber. And associated to such a thing is an on sequence, which we usually write in this way here. And if we write it as 1 plus n over 3 minus n, then we can associate to it a sequence of numbers obtained by substituting n equals 1, and then equals 2, and then n equals 3, and then n equals 4, and so on. And in this case, 1 and 2 is not problematic at all, but when n is 3, we can see that we're getting 4 over 0. And that's a new kind of phenomena, and we've decided to incorporate that with this new symbol, infinity, sort of a sideways 8 or a lemniscate. So here this symbol is a new symbol representing what up till now is an illegal fraction, the fraction 4 over 0. So a natural question is, can we meaningfully and precisely extend the arithmetic of the rational numbers to include a symbol like infinity? Is it possible to define 2/3 plus infinity, or minus 3 times infinity, or infinity plus infinity, or infinity divided by infinity, and so on? So that's where we're aiming in today's video. So one approach to this is to do it in stages, reflecting the natural order that we use to set up our arithmetic in the first place, starting from natural numbers to integers and then to rational numbers, or perhaps through fractions. So the natural numbers, the numbers 1, 2, 3, and so on, support the basic operations of addition and multiplication. And it's actually not hard at all to augment that system, say to nat with infinity above here. This sort of is going to be our new type, meaning that we're going to augment the natural number system by allowing one more symbol, the symbol infinity. And I emphasize again that this is nothing but a symbol, a typographical object, and it has no prior meaning, even though we give it the term infinity. That's only for really historical reasons. So the question is, how can we extend the operations? And it's pretty clear what to do. We're going to define n plus infinity to be infinity for any natural number n, or commutatively infinity plus n is also infinity. N times infinity, or infinity times n, will also be infinity. And when we add infinity to itself, we're going to get infinity, and when we multiply infinity by itself, we're going to get infinity. So basically, any operation involving infinity outputs infinity. This is a reasonable and consistent framework for doing arithmetic, which extends the usual natural number system. So a good exercise for you is to check that the commutative, associative, and distributive laws still hold in this extended number system, nat infinity. Well, a natural question is, why might we do this? Does augmenting the natural numbers by adding infinity actually have a meaning or use? All right, so there's a couple of ways of thinking about this kind of infinite object. One is that it might refer to a number that's so big that it overwhelms or exceeds any storage device that we have. If we're working with a system based on some physical computer, and we have to deal with a number that's so big that it doesn't fit on our computer, well, in some sense, we can't then address that number. We have to give it some special status. it's not unreasonable to call it something like infinity. On a more philosophical note, one could also maybe think about, what happens if, in principle, we conjure up larger and larger and larger numbers, occupying more and more and more space to write down, gigabytes, terabytes, hard drives the size of a galaxy, hard drive the size of the universe. Well, in principle, there ought to be natural numbers that are that big. And once we get numbers that are bigger than that, they become effectively almost invisible to us. We can no longer access them in any reasonable way, and it's probably not unreasonable to ascribe to them some number like infinity. So this is at least one way of enlarging our number system. All right, so we've added infinity to the natural numbers. How about adding infinity to the integers? So one approach to that is to mimic the construction of going from the natural numbers to the integers, described in Math Foundations 12, to go from these new augmented natural numbers, nat infinity, to, say, int infinity. So I'm going to leave this as an exercise for you to play around with, see if you can make something happen that makes sense. But a little bit of a warning, don't expect that all the laws are exactly necessarily going to work. Subtraction might be a little bit tricky to deal with. It's a new operation dealing in the integers that we have to worry about. But I'm not going to spend much time on this because my main thrust is actually in a different direction. I want to talk about extending rational number arithmetic to infinity. That's actually the application that has the most application to calculus. And that's what we're going to be talking about. So that's our main goal, is to extend rational number arithmetic from the rational numbers to what we might call rat infinity, where we've augmented the rational numbers. And we're going to introduce a new symbol, infinity, which is going to be written 1 over 0. And we'll also see that we're going to have need of another symbol, which we'll call star, which is 0 over 0. So we're going to try to set something like this up, and these are two objects that are necessarily going to figure in this story. And I know that you've all been taught and learned from an early age that 1 over 0 doesn't make sense and 0 over 0 doesn't make sense. Of course, that's in standard arithmetic. So what we want to do is we want to be able to enlarge the framework completely, consistently, and clearly so that we extend our meaning to these new symbols. And I remind you, this is not so much different from what we've done when we started going from natural numbers to integers. Right? We introduced negative numbers, which historically were very problematic. But we were able to introduce them very systematically just based on natural numbers, including this new notion of 0, which was a bit of a stumbling block for many civilizations to effectively introduce 0. And then to go to rational numbers, we again extended our arithmetic by doing something that formerly was not possible. In the integers, you can't divide 2 by 3. But then you introduce some symbols, some new framework in which 2 is divisible by 3. All right, so it's something like that, where now formerly you couldn't divide 1 by 0, that was not allowed. Now we're trying to think of a larger framework in which this might make sense. That's our goal. So of course this is a favorite subject for amateur mathematicians and people who are sort of philosophically inclined to try to create number systems where there's a division by 0 allowed. And every so often someone comes up with a framework for doing this. In fact, I think just a little while ago the BBC had a program about a mathematician in England who was teaching his students how to divide by 0. And the program presented this as something of a novelty. But in fact, this idea has been around for a long time. It's been around not perhaps in an arithmetical framework so much as in a geometrical framework. Okay. So if you know some projective geometry, then the idea of dividing by 0 is a very natural one geometrically. So we are going to be guided and motivated by projective geometry. And by anchoring our arithmetic to geometry, this somehow ensures that it's going to be stable and that it's going to be somehow natural. This is a very good thing to do, to try to connect arithmetic with geometry. So in some sense, this idea that I'm going to present to you now probably goes back in some form or another, a couple hundred years at least. Okay, so let me remind you of the plane, and with x and y coordinates. And I've drawn sort of coordinate lines here because I'm particularly interested in the integral points. Points like 2, 3 or 4, 6, which actually lie on the intersections or meets of these coordinate lines. So both coordinates having integer values. Okay, so let me remind you that one possible interpretation of rational numbers was as follows. We could think of the rational number line as actually the line y equals 1 in this plane. And that interpretation connects rational numbers with lines through the origin. So for example, the rational number 2 over 3, which of course is the same as 4 over 6 or minus 2 over minus 3 or minus 4 over minus 6, can be associated with this line. On this line, there are these integral points. There's 2, 3, there's 4, 6, there's minus 2, minus 3, there's minus 4, minus 6. These points correspond in an obvious way to those fractions. 2 over 3, 4 over 6, minus 2 over minus 3, and so on. Now, where this line meets the line y equals 1 is where you scale things so that the y-coordinate becomes 1. So you've multiplied a point, say that one there, so that its y-coordinate is 1. In this case, you would have had to divide it by 3. And that means that its x-coordinate is now 2/3. So this point right here where this line meets the y equals 1 line is the point that you might usually call 2/3 in a sort of primary school look at the rational numbers. So the rational number 2/3, which is sitting right there on the number line, can also be thought of in terms of this line through the origin. And can also be associated with this point. Or maybe this point, or maybe this point, or maybe this point, or many other multiples. As another example, say the rational number minus 5/3 corresponds to the point minus 5/3 over here. And but 5 minus 3 written that way would correspond to the point 5 minus 3. Or maybe minus 10/6, which would be further in that direction, or minus 15/9, which would even be further in that direction, and so on. And this line then that's associated to this rational number meets the number line y equals 1 at this point right here. And that is indeed minus 5/3 out. In other words, the x-coordinate really is minus 5/3. So what we have here is a situation where we're thinking about the rational numbers as manifested in a two-dimensional sense. And of course, if you've watched the last few videos in this series, about 5 or 6 videos ago, we were talking about the deep structure of the rational numbers. We talked about the Stern-Brokow tree. We talked about sort of a two-dimensional representation of rational numbers with wedges involved. So if you haven't watched those videos, please have a look to reinforce the idea that it might be useful to think about rational numbers in a two-dimensional sense. Okay, so when we do this, when we take this point of view, this projective point of view, and by the way, if you're interested in projective geometry, you can have a look at the Weil-Trigg series. Videos 31 to 40 roughly deal with projective geometry. And also my Math History 8 video talks about the history of projective geometry. That would be very useful in understanding some basics about the subject. So what we have here now then is the situation where lines through the origin correspond to rational numbers on the number line. You're given a line through the origin, then you just see where it meets the number line. That would be, say, at the point 2. This line would meet it at the point 3. This one at the point 4. This line at the point -3, at -5, and so on. So lines through the origin correspond to points on the number line. Almost, but not quite. There is one line through the origin which does not meet this y = 1 line. And that's the purely horizontal line, the x-axis. That's exactly parallel to y = 1, so it doesn't meet it. And so it's kind of natural to start thinking, well, as this point on the number line gets bigger and bigger and bigger, then it's clear that the line through the origin is getting closer and closer to this horizontal line. So it's natural to think about this line as representing infinity. And when we do that, well, the fraction 1 over 0, which is an illegal fraction, gets represented by the point 1, 0. That point right there in the plane. So when we talked about the Sternbrook-Hoe tree, we saw that this vector here played a natural role. There was actually a very useful place for this illegal fraction. So we're going to see more of that coming up here now. So the moral of the story is that if we want to extend arithmetic from the rational numbers to include infinity, we probably should think in terms of the projective line. We should think in terms of this two-dimensional picture where rational numbers get represented by lines through the origin. Okay? That's a very good way to think. So let's shift our point of view now from the rational numbers to integral points in the plane. There's a natural connection between the two, but they're different. But it'll be useful for us to think about integer points in the plane. So this is the type. So integer points. We're talking about points that are of the form a, comma b, where a and b are integers. And let's make sure we all understand that, right? Integers means natural numbers, or 0, or negative numbers too. Any one of those three possibilities is allowed. Now, if the second number is not equal to 0, then we can associate to this integral point, call it p, a rational number, the rational number a over b. So given a point like this, an integral point, where the second coordinate is not 0, then we can associate to it a rational number. Okay, so there's a natural connection here, which we're going to use later on. But now let's just stick with these integral points, and we're going to define some new operations. We're going to define some new ideas. Well, the first is not so novel. We'll call it scalar multiplication. We'll allow ourselves to write c times the point, and by that we mean just what you get when you multiply both coordinates by c. And c is an integer. If c is an integer and a and b are integers, then these two entries are still integers. So this is an integral point, and this will also be an integral point. And now we're going to introduce two new operations on points, on integral points, called rational addition and rational multiplication. And here are the definitions. So the sum, or the rational sum, of the point AB and the point CD is the point AD plus BC, comma, BD. And AD, of course, means A times D. So A times D plus B times C That's the first entry. And the second entry is just b times d. Now I hope this looks a lot like addition of fractions to you. This is exactly what we do when we add the fraction a over b to the fraction c over d. We get the fraction ad plus bc over bd. When we're dealing with fractions, we have to insist that the second entry is not 0, because we don't want to end up with a fraction that has a 0. But at the level of vectors, we don't care about the second entry being 0 or not. This definition makes sense whether or not one or both of the entries are 0. In particular, you could add 0, 0 plus 0, 0. That would be 0, 0. Rational multiplication is even easier. It corresponds also to the way we multiply fractions. So AB times CD is by definition AC, comma, BD. We multiply the two first entries, we multiply the two second entries. So these are just transcribing the usual notions of addition and multiplication of fractions to this related but different scenario of integral vectors in the plane. And we need one more definition that's going to be important for us. We're going to define the height of an integral point. AB to be B. In other words, the height of the point is just the y-coordinate, which geometrically in the plane is how high up above the x-axis it is. So now here is the main theorem to today's lecture. It's the theorem that asserts what are the arithmetical laws satisfied by these operations. So the theorem is that we have three integral points, P, Q, and R. They're integral points. The first statement is that P plus Q equals Q plus P, and P times Q equals Q times P. In other words, the order that we either rationally add or rationally multiply these 2 points does not matter. These are the commutative laws. The next one are the associative laws. They tell us that first, for addition, P plus Q plus R is the same as P plus Q plus R. And for multiplication, P times Q times R equals P times Q times R. So these are, of course, just exactly the same laws that hold for arithmetic with rational numbers. So the third laws are the distributive laws. And here they are. And if we look at this first one, if I remove this for a moment, then this looks just like the usual distributive law. P times Q plus R equals P times Q plus P times R. But what we're saying is that in order for this to hold in this situation, we need to multiply the left-hand side by h of P, the height of P. So the height of P, that's a number, times P times Q plus R equals P times Q plus P times R. And similarly on the other side, if we're having P plus Q times R equals P times R plus Q times R, we have to multiply here by h of R, the height of R. Now you can think about this as balancing things in some sense. The usual distributive law has 2 p's on this side, but only 1 on this side. This new distributive law has a p here, but also another p over here. So 2 p's on both sides. And similarly here. All right, so these are completely cut and dried laws that we can now check that they hold for integral points with these operations of rational addition and rational multiplication we've defined. And it's an excellent exercise for you to stop the video now, get out your pen and paper and say, I'm going to prove these. I'm going to check that these actually really work. Why are these heights coming in? This is unfamiliar. You can work it out yourself and see how they come up. A great exercise. Okay, so there's the exercise. Prove each of these laws. Let me prove one or two of them for you, the trickier ones. So let's have a look at associative law for addition. The law P plus Q plus R equals P plus Q plus R. So to prove this, we're going to suppose that P equals the integral point AB, Q is the integral point CD, and R is the integral point EF. A, B, C, D, E, and F are all integers. Any integers at all. Okay, we'll calculate the left-hand side. P plus Q plus R. First we need to calculate P plus Q. There's P and Q. The definition is AD plus BC, comma, BD. There it is there. And we have to multiply that by R. How do we multiply these two? Well, we take this thing here times this one, the product of the two outside ones, and add the product of the two inside ones, so BD times E. And then the second element is just the product of the second entries, BD times F. Fine, what about the right-hand side, P plus Q plus R? Well, there's P again, and now Q plus R is, there's Q, there's R. So the product is CF plus DE times DF. Now to add these, we need to take A times DF plus B times CF plus DE. That's the first entry. And the second entry is the product of B times the second entry DF. So are these two the same? Let's have a look. First entry here has an ADF. There's an ADF here. There's a BCF term here and also a BCF term there. And there's a BDE term here and a BDE term here. And both second entries are equal to BDF. So that associative law holds. And let's also have a look at one of the distributive laws. Say this one, H of P times Q plus R equals P times Q plus P times R. Again, we'll let P, Q, and R be as before. And then the left-hand side is H of P times Q plus R. So H of P is just the height of P, which is B. So we're talking about B times AB times the product of Q plus R. The sum of Q plus R is CF plus DE, comma, DF. All right, and this thing times this thing here. Well, we just multiply the A times this entry here, and then the B times this entry here. And we have to multiply all of that by B, and that means we have to multiply both terms by B. So I'll expand things out. So here there's an ACF with a B, and here's an ADE with a B. Here there's a BDF with another B, means B squared DF. So that's the left-hand side. Now the right-hand side, P times Q plus P times R. There's P times Q, P times R. So P times Q will be AC, comma, BD. We have to add to that P times R, product of this one with this one, so that's AE, comma, BF. So how do we add these two? We take AC times BF plus BD times AE. And the right-hand side is BD times BF, right there. So the first term here is ABCF, and the next one is ABDE. And the second term over here we have B squared DF. And when we've written it that way, we see these two are exactly the same. ABCF, ABDE, B squared DF. So these two terms agree, and the distributive law holds. So this being somewhat novel arithmetic, it's probably good to practice it to get it more familiar. So here's some exercises. Calculate 2, 3 plus 4, 5, 3 minus 1 plus 0, 2, 6, 0 plus 3, 1, and 4, 0 plus 0 minus 3. And a few calculations with products. 2, 3 times 4, 5, 3 minus 1 times 0, 2, just the same ones. 6, 0 times 3, 1, 4, 0 times 0 minus 3. These sums didn't have any of the 0, 0 points involved, so this exercise deals with that case. So show that 0, 0 plus any point A, B, no matter what it is always 0, 0. And similarly, 0, 0 times any point A, B, no matter what it is always 0, 0. So this 0, 0 point, which is a bit of a novelty perhaps, it has a very simple arithmetical structure. Anything added to it or multiplied with it just gives itself. All right, so now we're in a great position to connect this with this extended rational number arithmetic. So the point 0, 2 is going to represent for us the fraction 0 over 2, the rational number that we usually call 0. But this point here, say 6, 0, is going to represent a new kind of extended rational number, 6 over 0. So that's going to be acting like infinity for us. And this 0, comma 0, well, that's something even maybe more unfamiliar. So that's a new kind of element whose arithmetic is very simple, but which sort of plays an important role in connecting the arithmetic, in completing the arithmetic. So next video we're going to extend now to rational number arithmetic with infinity. I hope you'll join me for that. I'm Norman Wahlberger. Thanks for listening.